You are welcome to Physics Clinic. In this video, I will be discussing nuclear fusion. What is nuclear fusion? Nuclear fusion is a process in which two light nuclei combine or fuse to form a heavy nucleus with the release of a large amount of energy. The equation below represents a nuclear fusion reaction. Here we have two light nuclei, hydrogen 2 called deuterium and hydrogen 3 called tritium, combining together under very high temperature and pressure to produce a heavy nucleus called helium, plus neutron and energy are released during this reaction. In the sun and in stars, this reaction takes place there under very high temperature, and it is referred to as thermonuclear fusion. We are going to be looking at how to calculate for this energy that is released during this nuclear fusion reaction. This is an example of a nuclear fusion reaction. Here we are told that a nuclear fusion reaction is given by hydrogen 2 plus hydrogen 3 to give us helium plus neutron and energy. Then we are asked to calculate the quantity of energy released. And we are given the mass of hydrogen 2 to be 3.345 times 10 raised to the power minus 27 kilograms. We are given the mass of hydrogen 3 to be 5.008 times 10 raised to the power minus 27 kilograms. And the mass of helium is given as 6.647 times 10 raised to the power minus 27 kilograms. And the mass of neutron is given as 1.675 times 10 raised to the power minus 27 kilograms. And the speed of light, c, is equal to 3.0 times 10 raised to the power 8 meters per second. Solution. The first thing we are going to do is to calculate for the total mass of the reactant. In the equation, we are given hydrogen 2 plus hydrogen 3 combining to give us helium, and neutron is released plus energy. Now, hydrogen 2 and hydrogen 3 are the reactants, and the products here are helium and neutron. So the first thing we are going to do to find the energy released in this process, we are going to calculate for the total mass of the reactants. Total mass of the reactants, that will be the mass of hydrogen 2, which is given as 3.345 times 10 raised to the power minus 27, plus the mass of hydrogen 3, which is 5.008 times 10 raised to the power minus 27. So to adding these two together, we have 3.345 plus 5.008 all times 10 raised to the power minus 27, because 10 raised to the power minus 27 is common in this case. So when you add 3.345 and 5.008, we are going to have 8.353 times 10 raised to the power minus 27 kilogram. This is the mass of the reactant. So the next thing we are going to do is to calculate for the mass of the product. Mass of products. The product is helium and what? Nitrogen. Neutron, sorry. Now, the mass of helium is 6.647 times 10 raised to the power minus 27, plus the mass of neutron is 1.675 times 10 raised to the power minus 27. So when you add 6.647 and 1.675, we are going to have 8.322 times 10 raised to the power minus 27 kilograms. So this is the mass of the product. Now, if you look at the total mass of the reactant and the total mass of the product, you will see that the total mass of the reactant is slightly greater than the total mass of the product. This is because some of the masses of the reactant have been converted to energy. So the difference between the mass of the product and the mass of the reactant is the energy that is released during this process. And then the loss in mass is what we refer to as mass defect. So to calculate for that energy, the first thing we need to do now is to calculate for the mass defect. So we use the Einstein mass energy equation to now calculate for the energy released. Now, the mass defect, change in M, is equal to the mass of the reactant minus the mass of the product, which is 8.353 times 10 raised to the power minus 27, minus the mass of the product, which is 8.322 times 10 raised to the power minus 27. If you subtract it, you are going to have 3.1 times 10 raised to the power minus 29 kilograms. That is the mass defect. So now that we know the mass defect, we are going to use the Einstein mass energy equation to calculate for the energy release. And the equation is energy release is equal to change in mass and speed of light square. And the change in mass, which is the mass defect, is 3.1 times 10 raised to the power minus 29 multiplied by the speed of light square, which is 3.0 times 10 raised to the power 8 all squared. And that will be 3.1 times 10 raised to the power minus 29 times 3.0 square will give us 9.0 times 8 times 2 here will give us 16. So if you multiply out, you are going to have 27.9 times 10 raised to the power minus 13 joules. But in standard form, this will be 2.79 times 10 raised to the power minus 12 joules. So the energy released during this nuclear fusion reaction is 2.79 times 10 raised to the power minus 12 joules. This will be the end of our class on nuclear fusion reaction. In our next video, we are going to be looking at the difference between nuclear fusion and nuclear fission and the advantage of nuclear fusion over nuclear fission. Thank you.